The title of this webinar is CFD DEM coupling for modeling of fluid flow with accurate particle representation. So that's that is the key topic that I'll be covering during the next 30-40 minutes. Okay, but before I start, okay, I just want to say a few words about the industrial challenges, the motivation behind such a need. Okay, so for example, here on these slides, I'm covering within the process or chemical or oil and gas industry, there is a lot of needs and unknowns that we have to analyze, to study, okay, in order to predict the fluid flow with particles, and especially the ones where particle and particle to boundary interactions, they become relevant. They play an important role. So you can see here, on a drilling operation within a oil and gas well, during the production, you have to understand how the particles, how the drilling cuts are being removed, okay, along the annular on the well. Or, infiltration or separation devices, you have particles that can, accumulate, they can get, close to each other, they can actually cause some damage to the structure design of your equipment, okay, generating wear, okay, blockage in vibration, and different type of, phenomena that you need to understand and you need to model. And sometimes the only way to tackle this is through a lot of simplifications, because most of the solutions today, they cannot handle an accurate particle flow couple problem where particles are larger than the grid size, for example, or they have different shapes that are non-spherical ones. Okay, so what's the main topic here? Why do I have to handle the particle shape in a very and how do we do that? This is just an analysis here on the pure, let me say, particle representation. When you have a code like Rocky DEM, for example, that you can handle, this almond tablet shape here with just one polygon, and on the left side is what common and old technology DEM codes, they do handle the particle shape representation. They add spheres together, they glued spheres. That's how standard DEM codes they does, they do. Of course, when you have the real polyhedra representation, you have a more, difficult contact detection algorithm that needs to be implemented. Okay, but it becomes more accurate because you don't need to input within the code a lot of coefficients, okay, in order to represent, friction, or in order to take into account the edges, okay, because with polygons we can handle the sharp edges, so we can take the edges effect into account, which sometimes is important for you to accurate erosion analysis, for example, and I don't go without saying that, for example, if I want to model particle breakage, putting spheres together and then breaking them, it's a lot, requires a lot of modeling and simplification and extra efficiencies. When you do with the real shape, you start from a very good point to end up with a more accurate model, okay, when breakage model is necessary. Okay, so this is the key difference between Rocky DEM and standard or old technology, I would say, DEM codes. Okay, not only that, the DEM, discrete element modeling software and the technology, they're becoming more of a daily software, and a lot of that is a result of the multi-GPU processing. So we're taking advantage of the GPU cards available within the, these graphic boards and using them to do scientific computation. Okay, so Rocky has multi-GPU cards, okay, multi-GPU processing. And if you have the real particle shape feature, and you use your multi-GPU server, for example, or single GPU or multi-GPU processing to analyze that, it really becomes more feasible in engineering tool rather than, something that only R&D could use several years ago, and because the simulation was taking, weeks to finish. Okay? And if you can integrate these two technologies, the shapes and the GPU processing, with a very powerful simulation tool like ANSYS, you can approach a lot of interesting problems. Okay? And of course, you can add complex physics like the breakage model that I was telling before. When I say that Rocky has, particle shape capability, I want to go deeper a little here, and I want to tell you that our particle shapes is comprised of a family of, let me say, 3 elements. We have the 3D and the solid particle, like you can see here on the right, where we simulate the bottles. Okay, we can have 2D particles like shells. Okay, which you're seeing here, like as textiles coming from the through these roller cylinders. Okay, and we can have the 1D particle like fibers. Okay, so all of these are you seeing right now, they can be rigid or they can be flexible. Okay, so we added into our Rocky DEM software a family of elements which we have implemented an explicit finite element formulation in order to handle, the flexibility, okay, of each of these. Okay, so we have 1D element, 2D elements, and 3D elements like fiber, shell, and solids. Okay, within the code, and they're custom models. Okay, so just for you to have an idea of the fiber capability that we do have, this is a compression test that we did, comparing with some results that we also did, like stress strain responses of a box, full of hay, okay, which are these fiber elements here. So we're doing the compression of these fiber elements, and because of the fact that we have real 1D particles, we can handle high aspect ratio particle representation, which, is sometimes not doable if you just use the standard glued sphere approach. If I have, for example, 1 to 1,000 particle for Rocky fiber model, is just one particle, very, high aspect ratio, but it's still just one particle. If you use the standard glued spheres approach, you start with 1,000 of particles. Okay, so if I have like, 1 million of fibers, with Rocky, it's still just 1 million of fibers. If you have the glued spheres approach, when you have 1 to 1,000 aspect ratio fibers, you have, 1 billion of particles. So it's much faster, it's much efficient. And as you guys see here on the validation, it's also accurate. Okay, but of course, I can use that and use all the GPU resources to handle like the tumbling, okay, and the moving phenomena and the motion that happens in a tumbler polishing machine. Okay, when I have bolts and nuts, and I want to analyze the forces and the stresses within these particles in order to have a better polishing process. And this is we're talking about real polygons, convex and concave ones. So as you can imagine, you have a very complex search and contact detection algorithm, and we can come with accurate stress and responses here. And this was run in a single GPU, a P100 Tesla from NVIDIA. Okay, and we're getting results within a day in a very detailed and complicated problem, having up to 6 million faces, 60 million faces, which is a lot, something that people couldn't do that. Okay, and it now can do, and it's available in a commercial code. Okay, and we not only take advantage of single GPU processing, as I was saying, we use multi GPUs, and sometimes it's really a breakthrough in terms of performance and achievement. You can see here on the left side a plot that shows the relative speed up of several single GPUs and multi GPUs compared to a standard 8-core machine. So if I use Rocky in an 8-core machine for a given problem, I can wait for 91 hours using 8 cores. But if I put GPUs and even a 3 P100, which is not a recent one, I can reduce from 90 hours to 1 hour. So adding the multi GPU capability it's something that can make DM pretty useful for your engineering design process. Okay, and of course, when I do use GPUs or multi GPUs, it really depends on the number of particles, right? You need to have particles enough in order for you to justify adding more GPUs on top of each other. Okay, so if usually of thumb, if I go to with more than 1 million particles, I might go to a multi GPU approach. Okay. On top of that, you can add, and you can have all these particles breaking, not only the solids but the shells and the beams now. Okay, the fibers, right? And you have different breakage models, the ones that are more, that we call instant fragmentation. Within these models here from the left side, you are not too much concerned about, the crack propagation and the breakage, direction and the stresses. You're more concerned about the energy that you need to break, a given particle size distribution to another particle size distribution. Okay. Here on the left side, we have a more accurate breakage models, which, are more suitable for few particles or just, one particle. Which is similar to what you can see in a standard FA explicit codes. Okay, when we mesh the whole 3D volume of the particle and we break them, like, for example, you are dropping like a tablet and see what happens, or a box of tablets. Okay, so we have, more global models and more discrete, detailed breakage models. That's the message here from this slide. And not only that, we can also, as a key feature within Rocky, the capability to analyze what happens with the surface that is in contact with the particle that most of the times is suffering from abrasion, from erosion. So we can predict the surface wear modification while the simulation is happening. So we generate a surface mesh for the boundary, and due to the normal and tangential forces, we can predict using the Arcad's wear law the volume of material that is removed, okay, from the surface, and what is going to happen with the surface geometry during the simulation. So here on the right side, you can see the initial shape of what we call lifter here within this ball mill here. Okay, it starts with this, but it ends the simulation with a very smoothed surface here. And of course, we need to input some parameters, but the final surface modification, okay, the final surface representation is an output of the code. And you can, during the simulation, see that what's the effect, for example, on the particle lifting performance if I have this geometry change happening during the process. Okay, so Rocky can predict in a very accurate manner the surface wear that is happening within your process. So since I cover most of the features now, I'm now going into the ANSYS integration, okay, specifically with regards to the CFD integration. So codes like Fluent, you have different type of, modeling multiphase approach. You have the Eulerian approach, which treat the dispersed phase, the solid phase, for example, as a continuum media, or you can have a different class of models which treat particles as discrete particles. So Lagrangian models, for example. So Fluent has, DPM or DGDPM for dilute to dense systems. You have even Fluent DEM, models to approach, particle solid flows, okay? And when the particles are big, not, large in terms of particle count, but they are, big compared to the mesh side, Fluent has the NPM model, okay? But all of these are pretty much, tailored to spherical shapes only, okay? And it's hard when they have, complex physics with regards to particle-particle and particle boundary interaction. Rocky fits into this solution portfolio, adding shapes, okay, capability. So when I have a CFD and DM, a solid and fluid flow problem couple, and you want to add the particle shapes into account and a more accurate particle boundary representation. Okay, so for example, we have different types of coupling. You can choose the one-way coupling, for example, when the particle volume fraction or the mass fraction is not, big enough to affect the fluid flow. Okay, and you can see here, for example, particles are coming from the left with different sizes and shapes, and you have airflow, being pumped from the bottom here. So the difference between the lift and the drag and the weight of the particle, which dictates which particle should move up and which particle should move down. Okay, for example here, you can see that the brown ones and the blue ones with a more, particles that, surface that sees the fluid flow are the ones that are moving up. So you can compute here, for example, the separation efficiency, okay? And of course, I don't need to tell you that Rocky has shapes, and our coupling with Fluent has drag loss that takes the shapes into account. So we're not only doing the coupling, okay, assuming that all particles from the fluid flow perspective are spherical ones. You have different drag loss that can take shapes into account, okay? And if the number of particles move up with the mass flow and the rate of the, the particle concentration goes up, you can have, and you need to have, two-way coupling. So here on the right side, I can show you a fluidized bed application, which is a tight CFD DEM problem, okay? All the particles here that you are seeing are being simulated with Fluent, with Rocky, and the airflow that is coming from the bottom here, generating this fluidized bed, is being computed with Fluent. And for this application here, for each time step, Fluent and Rocky are exchanging informations. And not only that, I can add, as you can see here on the right, different shapes within the particle. And for example, I can see here a red ring that I'm adding within the particle bed, okay? And it's interacting with the airflow, it's interacting with the other particles, and everything here on the fluid flow is being computed with Fluent, and everything on the particle side is being computed with Rocky. Okay? So, as I was mentioning, you can have, particles in Rocky, and by design, we always had to take the particle shape when doing the CFD integration, the CFD coupling. So you can have, different drag laws for dilute and dense flows. You can add to the physics of the particles like different phenomena like adhesion. Okay, here you can simulate, for example, on the transportation, the pneumatic transportation of pellets of woods, but they have some humidity that I want to take into account. So as you can see, you have clusters of particles. Okay, and I want to simulate that with detail with regards to the drags and things like that. So this is also another simulation that we did with Rocky and Fluent. Okay, but the message here is that since Rocky has shapes, the coupling with Fluent takes the shapes into account, and we do have implemented into the code a library, okay, a library of drag laws that takes shapes into account. Okay, so a little bit of the highlights of what we do have, okay, today in our Fluent coupling. Okay, the one-way coupling and the two-way coupling, they have momentum and heat exchange. Okay, we have shapes into account. You can simulate with Fluent. Okay, Fluent, not only one fluid, but you can have multi-fluids like gas, liquid, okay, and particles. So I can have the particle distribution with different shapes immersed in the fluid. I can have the particle, with shapes within a free surface flow coming from the air and reaching the liquid surface and going through the media and, being transported and filling out the liquid effects as well. You can have that in rotating domains, and so we take moving meshes and interfaces into account. And on the processing side, the beauty of this integration is that you don't need to run Rocky in the same CPU that you are running Fluent. Rocky is somehow cloud ready or HPC environment ready. If you have GPUs available, Rocky can be used during the on the GPUs, and Fluent can use the CPU, so they do not compete for the same hardware resources while the integration is being done. So you can do a CFD DEM problem coupling Rocky and Fluent, and having Fluent using the CPU from your hardware and having Rocky using the GPU that you have available. Okay, so this makes the coupling efficient. Okay, another application here that we have done, for example, for a customer of ours, they were working on a coffee roasting machine. So we are in Italy. There is a big tradition of drinking coffee and the quality of the Rocky bean. So Rocky and Fluent can be used to represent the hosting, to model the hosting process. So you can see here on the left, cold coffee beans coming through these rotating blades here, and getting in contact with hot air that's coming from the bottom here. Okay, so on the left side, you see the Rocky simulation. On the right side, you see the results from the Fluent perspective. So you can see here, the concentration of the solids, or the velocity, of the gas. On the right side here on the top, you can see the temperature of the gas if the concentration of the coffee bean here are being represented or being seen by Fluent as this isosurface here, the gray ones. So within this simulation, I'm using a lot of good, interesting features. I'm using multi-domains, rotating domains, non-conformal and moving meshes, and taking into account conduction and convection heat transfer, okay, plus custom particle shapes. The coupling, okay, that we do, it's not only focused on the 3D solid elements. We also can do the coupling using our fiber particles. So one of our customers in the US, they have been using Rocky to simulate the flow of air plus hair, specifically hair coming from pets, because they design vacuum cleaner, okay, that are, you know, used to pet hair modeling. So you can see on the left side the experiment that they did to mimic the agglomeration of the air and of the pet hair, and you can see the same phenomena happening here when you have air and pet hair coming from the left of this cyclone, and the result, okay, you know, the amount of pet hair that, you know, is removed or being, you know, agglomerated and concentrated in the bottom part of the cycle. It is a very interesting application. It's a two-way Rocky and Fluent integration, and within the Rocky side, here we're using our 1D particle representation to model the pet hair behavior. Going to a more of an industrial phases here, with Rocky, you can simulate liquid and particles with different shapes and sizes, different shapes and sizes, and you have, as a result, a more accurate representation of the forces that the particles are applying on the surface of your domain. And because of the shapes and because of the corner and the edges effect, I can analyze the wear that is happening in certain key areas of my duct or my curve or my, you know, the bending, the band of my duct. Okay, so you can see that as time goes by, the wear or the amount of material that is being removed or can be removed depending on my coating or my duct surface treatment or protection device that I use, I can control and I can manage that. And the difference from Rocky to the other codes is that the forces and the stresses goes in terms of accuracy one level above because of the shapes and the edges effects that we are taking into account. Another interesting problem here, I have a filtering system where gas is coming with particles. And within this application here, I have a two-session filter device. I have spheres and cylindrical particles, and you can see the accumulation of the particles within the first and the second no filter sessions. And this is a two-way coupling, so on this next slide here, I can show you on the left the simulation without the particles, and where the particles are starting to settle down, you can see that the gas flow, the airflow, for example, here in this case, it changes the pattern. Instead of going through the central region of the filter, it starts, you know, feeling the presence of the solid phase here and start moving, you know, through the surroundings to the more outer regions of the filter. And on the plot here, you can see the effect on the pressure drop. Another interesting application that we can see here is with regards to the particle transportation. So let me say that I have a cavity here within the oil and gas industry, for example. I have to fill up an annular region with particles. And this is a liquid particle transportation system. So I put a few particles within the annular, and because of the interaction with the liquid that I'm filling in and the particles, I can see and I can predict how this packing is going to happen, where the, you know, how the filling is going to be done, how long it's going to take, what is going to be the final porosity of this media, you know, how efficient this filling is going to have. I'm going to end up with some dead zones where I do not have particles, for example. It's going to be a uniform filling. So all these are very tight particle and fluid flow problem we can analyze with Rocky. And I want to show here, I want to call the attention of the fact that you can have very dense systems, the fact that you can add particle shapes, the fact that you can have that the shapes of the particles and the particle itself, its concentration actually affect, you know, the fluid flow behavior. Another set of problems that we can model using Rocky and Fluent are the ones related to fixed bed reactors. And I can see them within chemical industry. I can see them within, for example, a blast furnace application, or a furnace, you know, a cement, or where I have to load and to feed particles with different shapes, different sizes and shapes. Like these type of, you know, particles here that I can see on the top, you know, complex shapes, you know, and how I put them together, how I organize them in such a way that I maximize the particle density, or I control the void fraction or the volume of the air, you know, because what I have to do here is to have an accurate geometric representation of the particle bed in order for me to do, you know, a CFD mesh on the void zones here, and then do a CFD analysis, computing mass transfer, heat transfer, and all the chemical reactions that I want. Sometimes I have few particles, but sometimes I have very dense particle systems with very complex shapes. For this case here, we have developed an integration with ANSYS that Rocky output is automatically transported into space clamp and ANSYS meshing. So a mesh can be done automatically as a result of this geometry here. And of course, with the mesh, I can then do a CFD analysis. So Rocky can be, and is being used by a lot of customers of ours as a tool that can provide a more accurate geometry for a CFD analysis, because geometry like this you cannot draw. You need to simulate using a DEM tool. And Rocky has shapes, so our final packing ratio, our final void fraction is more accurate than if I were just filling this cylinder here, for example, using glued spheres. So the last case here that I want to show is a fluidized bed reactor, which is a standard one. And for this case, I want to show more of a performance results, because a lot of questions that we get are related to the how long does it take? How it is compared to the CFD analysis? It takes much more time than the CFD run. Who is the bottleneck here? So we did a very interesting analysis here for a customer, doing 3 types of geometries: small, medium, large, moving from 100,000 particles to 10 million particles on the fluidized bed side, and on the CFD side, moving from a coarse mesh, starting from 52,000 cells up to 5.1 million cells. So there's 3 things that we did vary here on this feasibility study: the particle count, the geometry size, and the mesh, the grid size. So this is just one result to say, hey, we got consistent results, the pressure fluctuation. We cannot show the result, but there was a lot of validation. So you can see on the left, the pressure fluctuation, on the right, how Fluent sees the pressure and the solid volume fraction. This was for the small case. This is how, Rocky, the particle results, the particle behavior, the particle motion, right? But as we are analyzing the performance and the results, okay, of the speed, this is the conclusion here that I want to call your attention. So most of the times, especially if you have, to give you an idea, large meshes, 5.1 million, okay, cells, and if I have small or medium particle count, the CFD problem is the bottleneck, right? For the medium cases, if I have 1 million particle, for example, and just 52,000 cells on the CFD side, the DEM simulation is the bottleneck. But still maintaining the 1 million particle case, if I move from 52,000 cells to 500,000 cells, 520,000, the CFD becomes bottleneck. If I do not increase the particle count more, the CFD will always continue to be the bottleneck. But by the other hand, if I then add 10 million particles instead of 1 million, the DEM problem becomes the bottleneck. Of course, you can see a lot of good results in terms of scalability and performance. If I had more GPUs or more CPUs for the CFD side, I can manage that. But the key answer here is it really depends on how big is your CFD problem, how big is your particle count, how big is your CFD mesh, and what the resources in terms of GPU that you can use for the DEM solver, in terms of CPU that you can use for the CFD solver. As a result of the years of experience that we got dealing with our customers, we could see that I would say that most of the cases the CFD problem is the bottleneck, because I can apply a very engineering approach to model the particles, and the GPUs are faster. And the CFD problem sometimes, most of the times, our customers are doing very, very, very fine meshes, which somehow dictates the problem. So we are not slow, but sometimes we are as fast as the CFD solver can handle the problem without generating extra bottleneck on the DEM calculation. With that, I finish my presentation, and I hand it over to Christian. If you allow, Christian, we can receive some questions and do some, or answer those offline if there are some. Thanks for the opportunity, and it's with you, Christian.